Up until now, we've been talking about momentum problems in one dimension that happen along a straight line in the x direction or the y direction. Now we're going to move on to momentum in two dimensions. So with momentum in two dimensions, just like everything else that we do in two dimensions, it's going to be important to split up our stuff that happens in the y direction and our stuff that happens in the x direction. Our big idea here is that momentum will be conserved in each direction. We'll write that down because it's important. Momentum is conserved in each direction. So, find your initial momentum in the x, your initial momentum in the y, and it's going to stay constant all the way through the problem. That's really all there is in momentum in 2D. So in this case, every problem that has two-dimensional momentum really is two problems. It's the y problem and then the x problem that you have to do. So you're just going to take one problem, break it up into two problems, and you're going to get going with that. So for example, we'll do one that is strikingly similar to what I'm going to make you do tomorrow. So you're welcome for that. We have a ball. We'll say that the mass of this ball is 2 kilograms. I'm going to give this ball an initial velocity of 10 meters per second. That ball is going to hit another ball that's stationary. It has a mass of 3 kilograms and a velocity of 0. And the two objects are going to hit. After they hit, the red ball moves this way with a speed of, how fast did we say it was going? 10? With a speed of, 5 meters per second at a 53-degree angle. And what we're after is, what does the blue ball do? What is its velocity and the direction of that velocity? So, like I said, we got to break this up into the x and the y direction. So, we'll look at x direction stuff over here, and we'll look at y direction stuff over here. You know what's going to be easy? Y direction stuff. So, we're going to say initial, then final. In the y direction initially, the velocity of object 1 with his mass of 2 kilograms, so we have initially 2 kilograms. How much velocity does he have in the y direction? None. 0 meters per second. Plus object 2 with the mass of 3 kilograms and no velocity in the y direction. So that means initially I have 0 momentum in the y direction. I guess that's 0 kilogram meters per second. 0 kilogram meters per second in the y direction. Now, what happens afterwards in the y direction is a little bit interesting. So, we have to take this 5 meters per second at 53 degrees and look at the y part of it. So, 5 meters per second, 53 degrees. The y part of that is going to be 5 times the sine of 53. So using our handy-dandy calculators, 5 times the sine of 53 is 4 meters per second. So, the 2 kilogram ball has a speed of positive 4 meters per second in the y direction, plus whatever the 3 kilogram ball is going to be doing. We don't know yet. So, our equation is now starting to look like 8 kilogram meters per second plus 3 kilograms times our unknown y velocity for object 2. Well, boy, that's a horrible number. It's really easy to figure this out. We got negative 8 divided by 3 is equal to my velocity in the y direction. So my velocity in the y is 8/3, which is 2.66. I think, I'm just going to check that. Yeah, so that velocity in the y is negative 2.67 meters per second. Now I have the velocity in the y of this ball. That's one problem done. Now I have to do it in the x direction. So in the x direction, initially, I have a 2 kilogram ball moving at 10 meters per second, and it's going to run into the 3 kilogram ball that's initially not moving at all. So the initial momentum in the x direction is 20 kilogram meters per second. Now, after the collision, we've got to go back to this triangle and look at what part of this 5 meters per second at 53 degrees is in the x direction. So to do that, we're going to do 5 cosine 53. 5 cosine 53 comes out to be 3 meters per second. So that goes in my x direction stuff. Afterwards, the 2 kilogram ball is moving at 3 meters per second. And I'm left with the 3 kilogram ball, and I don't know what his velocity in the x direction is. So 6 kilogram meters per second plus 3 Vx. That leaves me with 14 kilogram meters per second divided by 3 kilograms. That's my velocity in the x, and that is a gross number. So 14 divided by 3 is 4.67 meters per second in the x. So I know the y component of the velocity and I know the x component of the velocity. So if I want the total velocity afterwards, we're going to go 4.67 meters per second in the x, and we're going to go 2.67 meters per second in the y, and that's down because it's negative. And so our resultant velocity, the one that we're really after in the whole thing, is right here. So that resultant velocity after the collision, our resultant velocity after the collision comes out to be, let's see, 5.38 meters per second at 29.8 degrees. And since it's south, it's 29.8 degrees. So we'd go back to this original problem and say, okay, our first vector came off at 5 meters per second that way. Our second vector in this case is going to come off at 5.37 meters per second at its angle of 29.8 degrees. And this is how you would do something in 2 dimensions. And again, this is very similar to what else we do in 2D, in that we separate things out into their x's and their y's and solve those problems independently and put them together where we can.